Good morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 4 Distribution Network OPF Analysis, and we have studied in the last class that how we can model the uncertainties for a random inputs to our OPF algorithm. So, today we will see how you can formulate the probabilistic OPF considering those uncertain events or those probability distribution functions. So, first we did identified the uncertain events, we plot them as a probability density functions. From there we have generated the scenarios using Monte Carlo simulation or Latin hypercube or point estimation method, and after that we followed some scenario reduction technique that Monte Carlo simulation will become easier to implement. Okay. So, today we will see how we can formulate the probabilistic OPF itself. So, let us say this is your deterministic loss minimization algorithm. This is the QOLP formulation, we already used it multiple times. So, you know that. So, this is the QOLP formulation which is minimization of the total network power loss. Inverter reactive power control to minimize the total loss. This is your power balance linear constraint, these are voltage linear constraints, you have voltage limit and you have your DER reactive power limit. Okay. This is your deterministic problem formulation. Now, we will see the probabilistic problem formulation. First, we have to define the objective or revise the objective depending upon the uncertain events. So, formulate a cost or performance metric that reflects expectations or risk under uncertainty. So, previously we have determined the deterministic value of the objective function, but now we have to deal with the expected value of the objective function. So, that is the first change we have to do with while designing or transforming a deterministic OPF to a probabilistic OPF. Second, model uncertainties represent key inputs such as load, renewable generation or as random variables or uncertain parameters with known distribution, that we have seen already in the last class how to represent and how to generate scenarios. Incorporate system constraints, include physical and operational constraints in probabilistic or robust form. Again, whenever you will go for the constraint formulation, you cannot put the deterministic formulation. You have to put it as a probabilistic or stochastic constraint. Because your objective function is also stochastic or probabilistic, your constraint must be also probabilistic and your input value also taken from a probability density function. Okay. So, for solving this kind of a problem, there are majorly three different techniques are there. First, stochastic optimization, second, robust optimization, and the third is chance constraint optimization. So, we will see one by one by looking at this method how we can formulate that problem like this and how you can solve it. So, first, stochastic optimization. In case of stochastic optimization, the control decisions under uncertainty by considering multiple possible future scenarios. That means, whatever scenarios we have generated, that S for 1 to 100 or 1000, okay, those scenarios you have to take into considerations, and considering all those scenarios, your cost function will be revised to the minimization of the expected value of that cost from all of those scenarios. So, you can see that previously it was only x, now it has become xs. That means, input data or uncertain parameter for that scenario only we are considering, and considering that you have to calculate the cost and you have to take the expected value for that cost. Okay. With the control, you have the u is the control decision, s is the random variables and xs is the state variable dependent upon that scenario. That means, for each and every scenario, if your load and DER generation changes, obviously your voltage and the power flow will change, right. So, that means each and every scenario will give you a different values of your state variable. So, that your state variable values are must be scenario dependent. Then you may ask, why then the control decisions are not scenario dependent? Because you cannot implement multiple solution, right, to a single control point. So, that is why you will take the expected value out of that control decisions. So, whatever control decision you will get from all of the scenarios, that should be an unique solution that you can feed to the proper component. Okay. Again, the constraints, the equality and inequality constraints you can see for each scenario, that is also dependent upon the scenario values. So, previously that is only a x equals to b and g of x equals to 0. Now, it has become x s. Also, the coefficient of that matrix or coefficient matrix also becomes scenario dependent. So, that is how we make the scenario and we implement it in the stochastic optimization. The accuracy of the stochastic OPF depends upon the quality of the uncertainty model and the representativeness of the selected scenarios. Obviously, that we have seen that if you generate more and more scenarios and you fit proper probability density function for a particular uncertain event, then you will get good solution. That means, if you fit the solar generation to the beta or wind generation to the variable, if you perfect fit if you have done and then you have generated scenarios in a very efficient manner, then you will get a very good solution for your stochastic OPF formulation and by solving it. So, using a large number of scenarios increase the accuracy, but also that raises the computation complexity. That is quite obvious, requiring a trade off between solution quality, time and tractability, that is required, and that is why we use that scenario reduction technique. So, that deterministic problem, if we reformulate it as a stochastic problem, so you can see it will be the minimization of the expected cost, total active power loss. And apart from these buses and the phases, you can see again another summation has been added, that is because of the scenarios. Okay? And as is expected, so there will be a probability value for each scenarios, and then you have your actual objective function, and there also your power flows are scenario dependent. Okay? So, again the cumulative probability you will get by multiplying how many probabilities you have, that we know from the probability theory. Again, in your constraints as well, you can see all the variables has become now uncertain parameter. We took this DER generation as the uncertain condition. So, because of this scenarios, your all the loading and all the loading scenarios, your power flow scenarios it also get changed. Same for reactive power and the voltage as well. Even the reactive power generation or reactive power support from your smart DERs inverters, that is also changing. Okay? And your voltage constraint also imposed with the scenarios. So, this is the overall architecture for your stochastic OPF. So, you can see or you have noticed that when we moved from the deterministic to the stochastic, we have added the scenario values here, and also we have added the probability values in the objective function, and that will give you the expected value of the decision. Okay? Now, what is robust optimization? Robust optimization is a mathematical approach used to make the decisions that remain feasible and effective under worst case realization. That means, other than considering all the scenarios, if we can formulate or if we can decide our control actions depending upon the worst case scenario, that is what will be the worst situation we can face, and we are preparing for it. If we are prepared for it, that means if any scenarios come lesser than that worst case, we are prepared for it. So, we need not to think of it. So, robust optimization says that you do formulate your probabilistic OPF as a worst case scenario condition. So, instead of optimizing the expected performance like the stochastic optimization, robust optimization finds a solution that performs well across all possible values of uncertain parameters within a predefined uncertainty set. Okay. That means, that will be working for, if it is working for worst possible scenario, that means it will work for the all intermediate states. Okay. In OPF problem, the uncertain parameter can be either at objective function or at the linear constraint or at the position of both, that we have already seen. Let us say you are trying to minimize the cost. So, that cost will be of energy cost, then your purchase substation purchase energy, then del T. If you have price uncertainty, then you have that uncertainty at the objective function, and previously we have seen you have uncertainty at the constraint when you are doing loss minimization. Now, if you do the cost minimization with the uncertainty at the load and as well as DERs, at that time you have uncertainty or the uncertain or random events at both the positions. Okay. So, depending upon where your uncertain parameters are there, you have to modify that equation by following the robust optimization framework. So, thus it aims, your robust optimization aims to minimize the worst possible condition arise due to uncertain events. That means, we are trying to minimize the maximum possibility or minimize the worst thing. So, worst thing means maximum hazard or maximum deviation. So, minimizing the maximum deviation will give you the worst scenario which is the best for you, okay, subject to all the deterministic constraint. Okay. So, this zeta is representation of the uncertain parameters belonging to the known uncertainty set, and we can define that uncertainty set as a box, ellipsoid or polyhedron. Okay. Then the significance of it, what is the significance? First, you do a minimization at the outer layer, that is trying to choose the best decision x from the feasible set. And the inner maximization says that nature picks, that uncertainty picks the worst case realization of the zeta. That means, if you are considering that your solar generation is varying from, let us say, 10 kilowatt, and it can maximum take a perturbation of, let us say, 10 plus minus 5 kilowatt, let us say, then what will happen? This zeta will be an uncertain event, and within this 5 flexible limit, it can take any value. Okay. So, that will maximize the value of your objective function by taking the entire range and find out where you will get the worst case scenario. You may get the worst case scenario at 5 kilowatt, you may get the worst case scenario at 10 kilowatt itself. So, where you will get the worst case scenario, where is the maximum probability or maximum occurrence of your worst case scenario, that it will consider, and after considering that worst case uncertain events, it will minimize its effect, and by doing this min max optimization process. So, the robust optimization uncertain variable constraints, let us say you have in the previous problem, if you see, we have the uncertainty at the constraint. So, we will go through with it. So, if you have an uncertain event Bij, if it is an uncertain parameter which is actually the nominal value, that is the forecasted value plus some perturbation or some uncertain parameter. So, this is your range of your uncertainty, and this is your actual positive represent the constant perturbation. That means, let us say that what I told, that it is a 10 plus minus, it is a random variable mu, or let us say random variable zeta, and then multiplied with a Bij cap. That cap may be 5 kilowatt. So, any value this zeta can take between 0 to 1 or whatever you are saying, or whatever upper limit you will give. Okay. So, highest, this is your maximum range for this actual value, and this zeta is an uncertain parameter. So, the optimization problem will be modified with the uncertain parameter at the linear equality constraint. So, this parameter, previously it was A x equals to b. Now, with this uncertainty, it has become A x equals to b prime or b this curve. Okay. Other things will remain constant. So, the linear equality constraint will be simplified, that now this b is what? This b, this is equals to your actual nominal value plus your perturb. So, you keep the nominal value to the left side. So, at the right side you have the worst case possibility, that is the maximum value of your b. Okay. So, if you write it in a element manner, then you will get Aij xi minus summation of this bi will give you the maximum of your, this is your uncertain parameter, signifying the uncertain parameter. Now, how you choose this zeta, that will give you that which uncertainty event or what is the level of your uncertainty event. So, that if you see that in the loss minimization algorithm, what we are trying to do, see there is no change in the objective function, only you can see the change in the constraint where you have your uncertain parameters, and here we have considering the uncertainty only at the load for the simplification, for the simplifying understanding. So, you can see only this load has been changed with this maximum zeta into beta cap b cap terms. So, this term has been added with your constraint and rest of the part is same. So, where is that only is that uncertain parameter, the robust optimization only consider or only changes that part, not like the stochastic one. Stochastic changes the entire formulation with the scenario, but robust only changes that part or that variable associated with the uncertain event. So, now how you can fix this zeta value, how you choose it, that will give you the how much good selection you did for the randomness for your uncertain event. So, in robust optimization, the uncertainty is handled deterministically by assuming that the uncertain parameters lie within a known uncertainty set. That means, we know what the maximum value your uncertain event can take or randomness with at the maximum level. What is the maximum level of your randomness, rather than assuming a probability density function. So, you need not to have a probability distribution function for a robust optimization, and that is mostly used when you cannot fit a good probability distribution function for your uncertain events. Okay. So, there are several classical definitions of uncertainty sets, and these are box, ellipsoidal or polyhedral. Okay. So, what is box uncertainty? Box uncertainty says that set represents the uncertainty by bounding each parameter independently with a fixed interval, forming a high dimension hyper rectangle. That means, if you have two uncertainties zeta 1 and zeta 2, then you will give a box for in their graph which has a maximum of xi. So, maximum level of your box constraint is says that this zeta value can take maximum xi value for all your uncertain parameters. So, if you represent that one as a equivalent robust counterpart of this equation, so this will be represented by a simplified linear equation. So, this is a simplified linear equation, and xi, this xi is adjusted to decide the level of uncertainty. So, if you want very high level of uncertainty, you put the xi value very high. If you want low level of uncertainty, then you put low values of xi. Okay, but this must be less than equals to 1. If you want very high uncertainty, then keep it at 1. If you want lesser value of uncertainty, then you keep it at 0.9, 0.5, 0.4 like this. Okay. Then the next set, that is called the ellipsoidal uncertainty set. An ellipsoidal uncertainty set models correlated uncertainties by bounding the uncertain parameters within an ellipsoid. That means, if you have a correlated uncertainty zeta 1 and zeta 2, then you form the bounding set as a circle or as a ellipse. Okay. This is circle or an ellipse, and the uncertainty set is given by your zeta is given by your square root of summation of your all zeta square should be lesser than a maximum limit omega. Okay. And depending upon that, similarly you can define the robust counterpart, where you will replace that maximum beta, this term you will replace with this term. So, again you will get some linear constraint, because these are all constant values. Okay. So, again you will get a linear constraint. So, previously this was equal to 0, now this has become equal to this value. So, therefore, all the decision variable values will also be updated to fit into this worst case possibility. Okay. That is why it is called the worst case possibility, because it has taken the maximum omega value and then your how much perturbation you are allowing. Okay. So, this omega is the adjustable parameter and suggested the range is less than equals to mod of root over mod of j, where mod of j is the size of the uncertainty set. That means, how many variables you have in your problem who are uncertain. So, if you have only load and d are uncertainty, then your mod of j is equals to 2. Okay. So, and depending upon that, you can choose your sigma value either less than equals to 2. That means, it will be either 1 or 2 or in between that any value. Okay. Then you have the next uncertainty set, that is called polyhedral uncertainty set. Now, what is polyhedral uncertainty set? A polyhedral uncertainty set is a set of uncertain parameters defined by a finite number of linear inequalities, forming a convex polyhedron in the parameter space. So, the uncertainty box will look like that. Okay. Similarly, you can represent the uncertainty polyhedron like the summation of all the uncertain parameters, or the zeta is less than equals to gamma. Okay. So, again you can represent it like this, where Wi is greater than equals to Bij. That means, again we are giving an adjustable parameter Wi, which will be greater than 0 and also which will be greater than your maximum allowable set, and we will reduce this problem as a linear problem. We can solve it, and this portion is first given as a deterministic. Previously it was equals to 0, now it is equals to an extra quantity, and that extra quantity will give you the worst possible case. Okay. So, this is why this uncertainty in the polyhedral uncertainty set is mostly used, because generally the uncertain events we do not know what is the range of it. Okay. So, depending upon that, this Wi value also will determine which is less greater than equals to your Bij. So, if your uncertainty what you have predicted, if it is also more than that, there is a possibility of it. If it is happening, then the Wi will adjust it. Okay. So, and sometime we also use the combination of them, like box plus polyhedral or ellipsoidal plus polyhedral. So, depending upon that, your uncertainty set or the boundary of that uncertainty will get revised. So, gamma is also an adjustable parameter, and similarly it is less than equals to mod of j. So, distinct feature of this robust optimization. The classical robust optimization formulation is use adjustable parameters, example xi, omega and gamma. So, you know, if you know these values to control the uncertainties, often constraining all uncertain elements in a constraint through a single shared parameter. That means, if you see in all the equations, only by knowing the gamma and zeta, xi, omega and gamma, if you know these values, if you can set these values properly, then you can solve your robust optimization problem. Okay. You need not to know so many things what we already did for probabilistic distribution, like stochastic distribution. You have to know the probability density function, then you have to sample it, then collate or concentrate them into few, and then you will be formulating your stochastic. But here, only by knowing that it will fit, your random event fit with which kind of uncertainty set, if you can fix it properly and then fix that constant value properly, then you can get the worst case solution possible. This leads to a joint control of uncertainty with the same constraint. That means, if there is, let us say, load and the DER, and load follows box constraint and your DER follows polyhedral constraint uncertainty set, this two you can accommodate in the single constraint by just modifying their part. Okay? You need not to modify the entire formulation, only that part will be perturbed with this concept. Okay? Potentially limiting flexibility in representing diverse uncertainty behaviors. Okay? So, robust optimization traditionally targets bounded uncertainty, through it can be extended to handle unbounded cases as well. Now, the last probabilistic OPF, attacking probabilistic OPF formulation is the chance constraint optimization. The chance constraint optimization incorporates uncertainty directly into constraints by requiring that they be satisfied with a specified minimum probability level rather than deterministically. Okay? That means, we will add and constraint with our problem as a probability constraint. We will see how it is done. It provides a flexible trade-off between feasibility and performance, allowing rare constraint violation in exchange for more efficient and cost-effective solution. Okay? So, you will give a probability very high probability maybe you give that this constraint has to be satisfied, whatever is your uncertainty, it has to be satisfied at 95% confidence level. So, there is only 5% chance that that constraint will be violated, and most of the time that will be satisfied. If that is satisfied, that means whatever uncertainty is coming, whatever level of uncertainty is coming, still your solution is feasible and still your solution is applicable. Okay? This approach is particularly useful when probabilistic information about uncertainties like demand generation is available or can be estimated. That means, for that you have to know that at which level your constraint will be violated. That means, demand or generation or prices, you know how much variation or maximum level of probability for your forecasted data. Okay. That means, you have to know that whatever my forecasted data, it has 95% confidence. Then only you can say that the constraint whatever I am putting as a chance constraint, that will also be satisfied in 95% confidence level. But before that you have to know that your forecasting data or forecasted data has 95% accuracy, okay, and you have to confident about that. So, this chance constraint optimization look like this. The inequality constraints on output variables are usually not rigid limits, but are rather soft constraints. So, if you have, let us say, V is less than equals to V min less than equals to V max. Whenever we write this kind of a constraint, inequality constraints, these are not very strict or hard constraint. This must be followed, but if it is a from 0.95 to 1.05 and your voltage falls below to, let us say, 0.94, that will not collapse your system. Okay. So, this you can say as a soft constraint, and it can be relaxed if you have a highest level of uncertain events. Okay. If it is deterministic, then you have to follow it. But if it is a stochastic event or if it is an uncertain event, then you can afford little bit of violation with this inequality constraints. So, therefore, this chance constraint will be only applicable to this inequality constraint, not with the equality constraints. Do not do the power flow constraints or power balance constraint with the chance constraint, that is never ever possible, because that has to be satisfied at all the time. You cannot say the power balance has to be satisfied at 95% confidence level. That makes no sense, because then that you are violating the physics of the system, right. So, only those constraints you can relax the violation of what, which is little bit permissible under the uncertain events. So, that is mostly the inequality constraints, not the equality constraints, because the voltage rule, that means downstream how much voltage will be reduced, or your power balance, these are only your equality constraints, right. That has to be satisfied all the time, whatever your uncertainty is, that you always have to satisfy. So, your chance constraint is always a inequality constraint. Okay. So, probability of that satisfying that inequality constraint must be greater than equals to a predefined probability value, that is mu, and normally that value ranges from 0.95 to 0.99. We are keeping it 0.99, because if it is 1, then we are saying that it has to be satisfied all the time. So, we are taking this probability to be 0.95 to 0.99. So, the optimization problem will be revised, your equality constraint will be intact, only the inequality constraint will be relaxed, and you can make it greater than equals to mu probability chance constraint. Okay. So, in our previous example, if we add this constraint, then only the nodal voltage limit constraint can be satisfied. You can do it the DERs as well, Q as well. So, probability of keeping the voltage limit within this V min square and V max square under the uncertain event as well is greater than equals to mu. So, that is how your chance constraint optimization is formulated. Now, how to solve this chance constraint problem? Previous stochastic and robust means ultimately you are going for a linear programming, right. But how you incorporate this probability constraint to a optimization algorithm and code it and then solve it? So, as far as till now there exists no software like which is a inbuilt commercial software which can solve this chance constraint optimization directly. That means, you will give it and with the probability constraint and it will directly give you the solution, that is not possible. So, we have to further simplify the problem. So, one simple method is to implementation of scenario based solution process. That means, you generate so many scenarios and check whether how many times you satisfied that constraint. You generate 100 scenarios and see whether your number of times you are satisfying that constraint is greater than 95 or not. If it is greater than 95, then you can say, yeah, the probability of assuring that that constraint is satisfied is greater than 95%. So, the idea is to approximate the chance constraint by enforcing it over a finite set of sampled scenarios drawn from the probability distribution function of the uncertain variables. The Monte Carlo simulation again will use to generate the samples from the probability distribution function of the uncertain parameters. After that, replace the original probabilistic constraint with the actual constraint, okay, with the scenarios. Okay. So, after that solve it and calculate the probability level by summing the probability level of each scenario. That means, you solve and get the values and see whether this is satisfied or not. Then each probability you add, okay, and you see that whether the summing probability is greater than the your ascertained or predefined probability or not. If it is so, then you can terminate the process. If it is not, then you have something wrong with the scenario generation, or you need to revise your scenario generation. Okay? So, then you recalculate it. The most optimal decisions are granted as final solution. From there, let us say you have 100 samples, and from there you got 100 scenarios, and out of them 95 or let us say 96 scenarios have satisfied. Then from this 96 scenarios, take the best one as your solution. Okay. So, this ends the module 4 of the OPF analysis, and I hope that you understand how to model the optimal power flow problem for the distribution network when you have multi-period constraints, you have uncertainty in place, and then how to proceed with the solution process. Okay. Thank you.